You know what GPUs love? One big, beautiful matrix multiply. In a dense transformer, your feed forward layer takes all your tokens, thousands of them, and runs them through one massive matmul. The tensor cores light up, utilization hits 95%. Life is good. Then, mixture of experts or MOEs came along. MOEs are ingenious. The pitch scale model capacity without scaling compute. The core idea in MOEs is to replace each feed forward module in a transformer block with multiple expert layers, where each of these expert layers is also a feed forward module, and use a few of them for each token. DeepSeek uses it. Mixtral uses it. On paper, multiple experts, like 256 of them, sounds incredible. Here's how it works. A router looks at each token and picks which experts should process it. Token 0 goes to expert 3 and expert 47. Token 1 goes to expert 12 and expert 199. Different tokens, different experts. Here's the dirty secret nobody warns you about. MOE training is a nightmare at research scale. Remember that one beautiful matmul? The router just shattered it into 256 tiny pathetic matmuls. Expert 0 gets 2 tokens. Expert 1 gets 0. Expert 47 gets 5. Tiny matmuls are the worst thing you can hand a GPU. Overhead dominates. Tiling is trash. Your expensive hardware is just twiddling its thumbs. Your $200,000 GPU cluster is running at 15% utilization. The flops are there, you're just not hitting them. We call these stranded flops, and 88% of your GPU is stranded. The fix is deceptively simple. Make each expert see more tokens per step. If you have 8 GPUs and each one routes a few tokens to expert 3, what if expert 3 saw all of them at once? Instead of 8 GPUs each running tiny expert batches, you pool the tokens. Send them to whichever GPU owns that expert. Now, expert 3 sees 8 times more tokens. Same model, same math, just smarter data movement. GPU utilization goes from 15% to 85%. That's replicated dense expert parallel, or RDEP. RDEP is a specific distributed topology. It consists of 3 parts. 1. Replicate the dense layers. Every GPU has a full copy of attention and embeddings. 2. Shard the experts. Each GPU owns a subset, maybe experts 0 through 31. 3. Dispatch tokens to expert owners. Return results back. The important part is the pooling step. If you have D GPUs, pooling makes each expert's batch look D times bigger without changing the model. Here's an important consideration. Without an all-to-all collective, how does each GPU know how many tokens are coming? RDEP uses a two-phase dispatch protocol. Phase 1, everyone counts. I'm sending 47 tokens to GPU 1, 23 to GPU 2. Write those counts directly to each destination. Then hit a barrier, everyone synchronizes. Phase 2, each GPU computes offsets with a prefix sum. Now everyone knows exactly where to write. Direct P2P writes via NVLink at deterministic offsets. This is not an all-to-all. The barrier syncs phases, not data. That's the key insight. Lightweight synchronization, not full collective communication. Zero nickel on the hot path. Speaking of barriers, we do them entirely on GPU. No CPU round trips. This pattern comes from DeepEP from DeepSeek. Each GPU has a signal array. When you arrive at the barrier, atomic add to your own signal, atomic sub from everyone else's. Then poll until all signals hit 0. That means everyone's arrived. No CPU, no nickel, pure GPU atomics. System scope memory operations make the writes visible across GPUs. This is what makes dispatch actually fast. Um, for RDEP, we need to auto-detect our topology and pick the right mode. Single GPU, just local sorting and padding, no communication. Multiple GPUs, one node, CUDA IPC over NVLink, 900 gigabytes per second, peer-to-peer. Multiple nodes, hybrid mode, IPC for local traffic, it's faster. NV SHMEM over InfiniBand for cross-node. So that's RDEP. Let's recap. The problem: MOE routers shatter your batch into tiny per expert workloads. Your GPUs starve for work, stranded flops everywhere. The solution: Pool tokens across GPUs before expert compute. 8 GPUs means each expert sees 8 times more tokens. Why it works. Tiny gems become fat. Gems. Utilization goes from sad to saturated. Router stability improves. More tokens per expert means less variance. Mixed precision overhead amortizes. Bigger batches make FP8 actually pay off. You can train DeepSeek shaped models without DeepSeek sized clusters. Same model, same math, just smarter data movement. So, for a great implementation of these ideas, the code is in the awesome NMOE open source library, and its link is in the description. For the next video, FP8 and NVFP4 experts, mixed precision sounds great until overhead eats your gains. We'll try to learn why overhead is the enemy and how to make it disappear. Thanks for watching. If this helped, please like and subscribe. And if you build something cool with RDEP, let us know. See you in the next one.